Hi everyone, today I'm going to present a tutorial on CFD simulation of a wind turbine using STAR-CCM+. The simulation setup is performed in the following steps: definition of the computational domain, definition of the regions, mesh generation, definition of physics and boundary conditions, definition of monitors, solver settings and stopping criteria, and at the end we have post-processing. What comes next is a detailed explanation about each of these steps. So first, the definition of the computational domain is given. First, you need to create a new simulation here. Here you can also choose the number of cores to be used in your simulation, and this number must be smaller than or equal to the number of cores available in your PC. Go ahead and click OK. From here you can save your simulation. I'm going to call it wind turbine simulation. For this tutorial, I'm going to use the horizontal axis star-regulated two-bladed NREL phase 6 wind turbine. You can access the geometry using the link given in the description of this video. You can import directly your wind turbine geometry into your simulation using File. Here we have import surface mesh. And select your geometry, which is here. Go ahead and check the check parts validity and repair invalid bodies. Click OK. Under parts, expand the NREL phase 6 geometry, which we can see here. Okay, right click on body 1 and rename it to rotor. Right click on body 2 and rename it to tower nacelle. The present simulation involves the rotating blades of the wind turbine at the center and stationary outer boundaries, which represent the wind tunnel walls. Such flows can be best resolved through the use of a combination of rotating and stationary meshes. There are two main options as shown in this figure here, which can involve either an overlapping overset mesh, where a rotating cylindrical mesh is superimposed on a stationary Cartesian mesh, or the sliding mesh method, where a rotating cylindrical mesh at the center slides past a non-overlapping outer stationary mesh. While the transfer of information across the two meshes is more complex in the case of the overset mesh than in a sliding meshes, grid generation is much simpler. Generally, it is recommended to use the sliding mesh technique for geometries which we have known rotating rotational velocity. Note that as the interface in the sliding mesh approach splits the flow field into two separate domains, it is very significant to update the values of the variables at the interface frequently throughout the simulation. So to create the cylindrical rotating subdomain where the rotor will be located, go ahead and right click on parts, new shape part, cylinder. For the start coordinates, put 0, 0.3 and also 0. For the end coordinates, put 0 and minus 1.25725, and again 0 for Z. For radius, put 7.5435. Okay, and note that this value of radius is equivalent to 1.5 times the radius of the turbine rotor. So now click create and close. You can drag and drop this cylindrical part to geometry scene. You can choose the orientation from here, right? Put X positive and minus Z. For further configuration, you can use this part also. If we make everything transparent from here, we're gonna be able to see that the rotor is fully contained in the rotating cylindrical subdomain. The next step is to create the outer stationary domain, which represents the wind tunnel, as we are replicating the experiments performed on the NREL phase 6 wind turbine. The dimensions of the computational domain should match those of the NASA wind tunnel. So right click on parts, new shape part, block. Okay, here we have two corners. For corner 1 we put minus 18.3 minus 20.116 and minus 12.9. For corner 2 we put 18.3 150.87 and 11.5. So click create, close, and here we have the block. We're going to call it wind tunnel. To define boundary conditions on each wind tunnel surface, we need to split wind tunnel surface. Okay, expand the wind tunnel here, then surfaces, block surface, right click on it and split by patch. In this dialog we can see all the wind tunnel surfaces. As we select a part surface from here, the corresponding surface is highlighted in the geometry scene, as we can see here. Select the first one and put it, and go ahead and rename it bottom. Click create, Second one is inlet, create. Third one is side, create. Next one is clear the outlet, create. Here we have top, create. And for the last one, we close the dialog and rename the block surface to side 2. For post-processing, it is useful to split the rotor surface in various parts using the split by patch technique. So let's select let's select the rotor, okay, here, and use the reset view, expand rotor, expand surfaces. We have here faces. Now split by patch. We have two surfaces here, okay. These two surfaces here, we multi-select them and go ahead and rename it to left blade base. Click on create. Now we have left blade here, right blade base, click create. Right blade, click create, and the rest we're going to call them as hub. Let's also rename the surfaces of the cylindrical rotating subdomain. We can rename it to cylindrical rotating subdomain. Go ahead and expand the cylindrical rotating subdomain under surfaces. Right click on cylinder surface, right, and rename it to rotating part. Now we need to subtract the rotating subdomain from the wind tunnel. So go ahead and multi-select both rotating subdomain, right, this one, and the wind tunnel. Right click on one of them and select Boolean, subtract. Select the wind tunnel as the target part and click on OK. So multi-select the subtract and nacelle, tower nacelle from here, right, these two together, and again right click on one of them, select Boolean, subtract, target, put subtract as target part, and click OK. Now we have the subtract 2, which is in fact our virtual wind tunnel. We're going to name it to virtual wind tunnel. Okay. Another Boolean subtract operation that we need to perform is to subtract the rotor from the rotating subdomain. So again, we need to multi-select rotor, right, and the cylindrical rotating subdomain. Go ahead and right click on one of them, select Boolean, subtract, and the target part this time is cylindrical rotating subdomain, right, and click on OK. Again, right click on subtract 2 and rename it to virtual rotating subdomain. To view these parts, right click in the empty space of the graphics window and select hide all parts. Now select the virtual wind tunnel, which is this one, and virtual together with the virtual rotating subdomain, and drag and drop them into the geometry parts. So we can use the transparent technique from here, right, and we can see our computational domain. So now we created the parts. We go ahead and right click on them, first on virtual rotating subdomain, click on assign parts to regions. First create a region for each part, select create a boundary for each part surface, and here select don't create interfaces from contacts, click apply. We need to do the same for the virtual wind tunnel. We can select from here and click apply. We can visualize the regions from here, right, under regions, expand regions. We have the both regions here, right, the virtual rotating subdomain and the virtual wind tunnel. As we can see here, also the boundaries. Let's now create the mesh. Before we start the process of creating the mesh, it is useful to define the interface between the two domains. So go ahead and expand the regions as we have already done here. Expand both the virtual rotating subdomain, right, and the virtual wind tunnel. Multi-select the rotating part boundary in both regions, rotating part here and the rotating part here, right. Right click on one of them and create interface. Okay, so to create mesh, right click on continue here, new mesh continue. Okay, we're going to assign the mesh 1 here to virtual rotating subdomain. Right click on models and select meshing models. We surface measure, trimmer, also prism layer mesh. Close from here. So go ahead and expand the models, click on trimmer and activate here, do mesh alignment. Now under reference values here, leave the base size value as its default value. Set the maximum cell size here to 100. Set the number of prism layers here to 15. Prism layer stretching here, set it to 1.1, and under prism layers thickness, set the size type to absolute, right? And set the absolute size to 5 centimeter. Under surface size, set both the relative minimum surface size and relative target size to 0.55, 0.55. Under template growth rate, set both the default growth rate and boundary growth rate to slow. Now let's set the mesh size values on the domain boundaries. Go ahead and expand the regions, which is already expanded. Then the virtual rotating subdomain, which is here. Under boundaries, multi-select blade, right blade and left blade, and also left blade base, right blade base, and right click on one of them and click edit mesh conditions. Check the custom surface size. Under mesh values, put 0.55 for both relative minimum size and relative target size. Click close. Now select hub, expand hub, check the custom surface size, and then under mesh values, put 2.2 for both relative minimum size and relative target size. Click on customize prism layer and set it to disable. Now select the rotating part here. Check the custom surface size, and then under mesh values, put 11 for both relative minimum size and relative target size. Click on customize prism layer and set it to disable. Now go ahead and create a second mesh continuum to be assigned to the virtual wind tunnel. Right click on models and select meshing models. We're going to select surface remesher and the tremor. Close. Expand the models, trimmer, and check the do mesh alignment. Under reference values, leave the base size value as default. Set the maximum cell size to 400. Under surface size, set both the relative minimum size and relative target size to 0.55. Under template growth rate, set both the default growth rate and boundary growth rate to slow. Now let's assign the second mesh continuum to the virtual wind tunnel. Click on virtual wind tunnel, and from here mesh continuum, select mesh 2, expand virtual wind tunnel. We need to now let's the mesh size values under domain boundaries. Okay, under boundaries we need to multi-select bottom, inlet, outlet, side 1, side 2, top, and right click on one of them and click edit. Here select the custom surface size and put both the relative minimum size and relative target size to 400. Close the dialog. Here faces, let's rename it this to tower nacelle. Now let's expand the tower nacelle, mesh conditions, custom surface size. Let's check this dialog, and here in mesh values set 2.2 for both the relative minimum size and the relative target size. Now we need to set the mesh on the rotating part here. It is better to use the same mesh settings that we used for this part in the virtual rotating subdomain. Okay, so let's expand rotating part, expand mesh conditions. Here on custom surface size, check the box here, and mesh, let's set 11 for both relative minimum size and relative target size. Now we set up the mesh for our simulation. Go ahead and click on generate volume mesh from here. To visualize the mesh, go ahead and right click on scenes, new scene, mesh. We can change the orientation. Click here, right, on view, views, and then go ahead and click on -X and -Z. So that's it. Right click on drive parts here, new part, section, plane. Set the origin to 0, 0, 0, and set the normal to 1, 0, and 0. No displayer, and then click create. First right click on the empty space here in the mesh scene 1 and hide all parts. And now drag and drop the plane section into the mesh scene. We can see clearly here the mesh we created around the wind turbine and in the computational domain, right? We can add the wind turbine geometry, right, to the mesh scene. Go ahead and expand mesh scene here, and here right click on displayers and select new displayer, geometry. Select geometry here and uncheck here, deactivate the outline and activate the surface. Expand geometry, parts, select here all the wind turbine geometry, right? Hub, left plate, right plate, and from here you can select the tower nacelle. Click OK. You can also here select the color of the geometry. Color mode here, you have to first select geometry and color mode, set it to constant. After that, put it to constant, and color here, set it to a more distinct color. I would choose this color here. We can configure the mesh scene this way for us to see better the mesh and the geometry. You can export the mesh scene for later creating animation from the exported images. For this purpose, expand attributes, and first background color, let's put it to solid. Here click on update, click on save to file, output directory. Here you can create a new file and rename it to mesh. Click OK. We can select mesh here by entering into this file and click OK. Set the trigger to time step, and from here set the time step frequency. Expand, right? You need to expand, update, and time step frequency. You can put it to 2. And hard copy, click on hard copy and put it to 1200 and 900. Okay. Expand annotations here. Logo, you can click yeah, right, you can deactivate the visible, and also expand tools and annotations from here, and drag and drop solution time into the mesh scene here. Okay, so put it, you can choose where you want to put it. I think it's better to put it here, close to the coordinates, right? And here you can also click on background, right? If you put so you can put it anywhere you want in the scene. Now let's create the physics and define the physics that we're gonna use in our simulation. Under continua, under physics, right click on models and select models. We're going to use an implicit unsteady solver. We're going to use gas, a segregated flow solver, a constant density, turbulent flow. Now here is a tricky one. To better account for the turbulent flow 3-dimensionality in case of wind turbines, we're gonna use a Reynolds stress turbulence model. Later in another video in my channel, I'm gonna explain thoroughly the various types of RANS-based turbulence models and their advantages and disadvantages. We're gonna select the elliptic blending type of Reynolds stress turbulence model. Close the dialog. Under initial conditions, select velocity and put it 25 in the y direction. Now under tools, right click on motions, right, new, and rotation. Set the axis direction to -y, axis origin 0 0 0. Rotation rate, set it to 72 RPM. Here you can also create a local coordinate system and assign it to this rotational motion. This way the coordinate system will rotate with the same rotational velocity as the value we set here. So under coordinates here, coordinate system, expand laboratory, local coordinate system, right click on local coordinate system, new, and Cartesian. Okay, you can set all the values as default values and click create. Here we have a local coordinate system, Cartesian 1, which is a local coordinate system that we're gonna assign it to this rotational motion, right? Click on rotation, and here we have managed coordinate systems, and we're going to put it to coordinate the local coordinate Cartesian 1. Now to assign this rotation to the virtual rotating subdomain, let's expand here regions, virtual rotating subdomain. Here under physics values, motion specification, we're going to, under motion, right, we're going to select rotation. Okay, now let's define the boundary conditions. Expand virtual rotating subdomain, expand boundaries. Okay, select the rotating part and set the type to symmetry. Now expand virtual wind tunnel here, multi-select bottom, inlet, bottom, rotating part, side 2, top, and set all of them to symmetry plane. Okay, here we have inlets. Click on inlet and set the type to velocity inlet. Expand this boundary, and under physics values put the velocity magnitude to 25 meter per second. Click on outlet and set the type to pressure outlet. Expand outlet under physics values. Okay, pressure is already 0. This is the relative pressure, right, with respect to the absolute pressure. Now let's define the solver settings. Under solvers, the time step that we're gonna use corresponds to a rotation of 0.5 degrees per time step, which is equivalent to 0.001157 seconds. Set the temporal discretization scheme to second order. Go ahead and save the simulation. Under stopping criteria here, set the maximum inner iteration to 10 and the maximum physical time to 3.33 second, which is equivalent to 5 complete rotor rotations, and check the maximum steps. Now right click on reports, new report, force 1, rename it to thrust, set the direction to y positive, check the smooth values here. If you cannot see the properties here, you can activate this from here, Windows, right? Window and properties. Set parts to blade, right? The left and right blade, left blade, right blade. Now create another report that will be a moment report, right? A moment, which is here. Right click on moment 1 and rename it to torque. Set the axis direction to y negative, right? 0, -1, 0. Check the smooth values again. Here, so we need to set the parts to left blade, right blade. Now right click on both of them and right click on one of them and create micron plot and select multiple plots, one per report. Now let's create a scene, right, where we can visualize both the wake behind the wind turbine and the velocity magnitude of the flow, right? First, go to drive parts, expand drive parts, right click on new parts, ISO surface, set the parts to all the domain, right? Here under scalar field, select Q criterion and set the value here as 5. So we are set here, all is set. Now let's right click on scenes, new scene, scalar, expand scalar here, under displayer, under displayers here, click on outline 1, uncheck at outline, check surfaces, okay, expand outline here, and set the parts to the wind turbine geometry. Set the color here. We can also here we can choose color mode to constant and then set the color to a more distinct color. Change the orientation to from here view, right, views -X and -Z. Put it more closer, okay. Now click on scalar here, scalar 1, set the contour style to smooth fill. Now expand scalar 1, set parts to isosurface that we just created. Set scalar field here to velocity. Magnitude, okay. In this case again, you can export the scalar scene for later. At the end we have the post-processing, okay. It is worth mentioning that the computations are performed on a desktop computer consisting of 64-bit Intel processors i9 with a velocity of 3.6 gigahertz and 64 gigabytes of RAM. The simulation takes almost 12 days to finish because we are using the Reynolds stress turbulence models. We could use some turbulence models that would take much less time. Okay, I'm going to explain further the various types of RANS based turbulence models in another video, where I'm going to discuss these aspects also. Here we can see the wake field around the wind turbine. However, it is worth mentioning that to capture the wake field like this behind the wind turbine, the mesh is refined inside a cylindrical region, as is shown here, okay, which I called far wake. This region has the same radius as that of the rotating subdomain and extends from upstream of the rotating subdomain to 3 rotor diameters downstream of the wind turbine. Okay, the mesh size inside this region is maintained 11% of the base size. Note that this is the same size that we have used on the interface between the two domains, okay, the rotating subdomain and the virtual wind tunnel. We can see here the behavior of the residuals, okay, and we have here the thrust force. We can zoom in to see better the behavior of the thrust force, okay. As can be seen, the thrust force has an oscillatory behavior, which is due to the vortex shedding around the wind turbine blades, as which we can see clearly in this figure here. And we have the torque here, right, which again has an oscillatory behavior. Note that the reason that we use this particular wind turbine is the availability of a large amount of measurements at different operating conditions, so we can simply use this experimental data to validate the CFD simulations. This is the end of this video. I hope you found this video useful. Please let me know what you think about this video by leaving a comment in the comment section. Thank you for watching the video, and for further upcoming videos, please subscribe to this channel.